So let's talk about what this diagonalization business has to do with linear transformations. Because what we're doing is just factoring a matrix into a product. So we're just factoring the matrix A into this product. And we know multiplication by a matrix is going to give us a linear transformation. So multiplying by these three matrices is also going to be a transformation. It's going to be 3 transformations. And each of these matrices does a thing. So notice that the columns of P, because we have this linearly independent, because P has linearly independent columns, because P is invertible, the columns of P form a basis for R2. Since P is invertible, the columns of P form a basis for R2. Since P is invertible, the columns of P form a basis for R2. That's the invertible matrix theorem. Since P is invertible, the columns of P form a basis for R2. I'm going to give it a name. I'm going to call it B. 1, -2, 1, -1. Remember that a basis should always be a set of vectors. So squirrely brackets, and then vectors separated by commas. I made the unfortunate choice not to name these 2 vectors. Oh well. So since P is invertible, the columns of P form a basis for R2. Moreover, the matrix P is the change of coordinates matrix from standard coordinates to B coordinates. P is the change of coordinates matrix from B coordinates to standard coordinates. That means that the matrix P, just those vectors in columns, since those are the standard coordinates of the B vectors, P is the change of coordinates matrix from B coordinates to standard coordinates. So if I have B coordinates of a vector X and I multiply by the matrix P, I end up with the standard coordinates of X. So if I have B coordinates of X, multiplying by P turns them into the standard coordinates. Multiplication by the matrix P takes B coordinates and turns them into standard coordinates. What that means is that P inverse will turn standard coordinates into B coordinates. P inverse is the change of coordinates matrix from standard coordinates to B coordinates. So if I take standard coordinates and multiply by P inverse, I end up with B coordinates. So if the matrix P turns B coordinates into standard coordinates, the inverse of P will turn standard coordinates into B coordinates. That's just cool. The inverse does the inverse of what the original does. The matrix P turns B coordinates into standard coordinates, so P inverse should turn standard coordinates into B coordinates. If that didn't happen, none of this would be very useful. So let's draw the picture of linear transformations. If T, let's let T map R2 to R2 be given by T of X equals AX, where A is equal to this matrix, 7, -4, 2, 1. So let's think about linear transformations. We know that since this transformation is given by matrix multiplication, this is a linear transformation. And if we look at R2, and it goes from R2 to R2, and X gets over to AX. And here's R2, and this is also R2, where the image of X is just AX. So this is the picture that we've seen before, and we've seen R2 in standard coordinates. So also notice that A is equal to P times D times P inverse. So I'm going to need, I should have made smaller R2s. Also notice that A times X is PDP inverse times X. So A times X, oh it fits, is equal to P times D times P inverse times X. Because we know that A is diagonalizable. So the first thing that happens to the X, if I multiply this out, is I get PD times P inverse times X. And P inverse takes standard coordinates and turns them into B coordinates. So this first multiplication, if we multiply it by P inverse, that takes X and writes the B coordinates of X. So this top line is going to be R2 in standard coordinates. And down here, the second line will be R2, but in B coordinates. And multiplying by P inverse is what turns standard coordinates into B coordinates. Now the transformation is going to go, we have to apply the transformation. And that in B coordinates, multiplication by A is just multiplication by D. So this is equal to P times D times the X coordinates, or sorry, the B coordinates of X. So now we'll go over here, and this will be taken care of with multiplication by D. Whereas in standard coordinates, this was taken care of with multiplication by A. And so over here, we're going to get D times the B coordinates of X, which will be, as we can see, the B coordinates of AX. So this is going to be, oops. So d times the b coordinates of x will get us the b coordinates of ax. And then we're going to multiply by the matrix P, and the matrix P turns b coordinates into standard coordinates. Multiplying by P turns b coordinates into standard coordinates. So, makes sense. AX is PDP inverse. Multiplying by P inverse turns standard coordinates into b coordinates. Multiplying by D performs the action of the transformation. Oops, that's down here. And then multiplying by the matrix P gets us back into standard coordinates. Any questions? This is what was going on in 4.7 when you were doing all those problems where you were writing the c coordinates of a vector, and the inverse goes from standard coordinates to b coordinates. If this R2 had been in some weirdo coordinates like c coordinates, multiplying by p inverse would change it to b coordinates. Multiplying by the matrix D would would give you the images, and then multiplying by p would turn back into c coordinates. So that's how all those coordinates are connected. Any questions? So if we pick a value for x, we should, and we find p inverse, what we could do is find ax and show that it maps over under t. But then we can also do p inverse. That will multiply by p inverse. That would find the b coordinates of x. Then multiply by the diagonal matrix D to find the image in the b coordinates. And then multiply by p to get back to the standard coordinates. Right. Let's pause the video here. Stop the video here and talk about next steps.